this paper, which is efficient streaming language models with attention sinks, which is authored by Shao et al. So, show of hands, who has seen this movie? Yeah, that's quite a lot of people. So, for those who don't know, this movie depicts the story of a lonely writer who develops an intimate emotional relationship with an advanced AI system called Samantha. In other words, it's just an AI girlfriend. So, similarly, imagine there's a CMU student here who's single and he wants to chat with his AI girlfriend. He chats with it every day and he's sharing almost every aspect of his life. And then, just when the AI girlfriend is about to say the words, I love, okay, that's when it just dumps some pile of words here, and my pal's all heartbroken. So similarly, there are like multiple instances in the real world where language models cannot handle long conversations. And some of these struggles basically include that, it takes longer time to process input tokens and calculate attention scores. Second is there's increased usage of memory to store tokens and also to store attention scores. And finally, continuous prompting would exceed the context length of the language model, leading to more incoherent and out of context responses. So first, I'd like to talk about the current attention mechanisms that are there to address either one of these problems. First, I will discuss the dense attention. So let's consider this famous quote, "My heart is in the work" by Andrew Carnegie, and assume that we are using word-level tokenization in this particular sequence. So during the calculation of attention scores, each word attends to the tokens that precede it, and simultaneously their key value states are stored in the KV cache for future token generation. So this enables the generation of new tokens by taking the context of the previous ones. So as you can see here, we've depicted with a small animation. Now, the drawbacks include that there's a quadratic increase in the memory and computation if the sequence length increases. So moreover, longer sequences or more prompts can exceed the language model's context length, leading to incoherent outputs. Now let's discuss about the window attention, which is again kind of similar to dense attention. The only difference is it operates on a fixed window, which we have depicted in blue. And then let's just say that window size is 3 here. So this approach is similar to dense attention, as I've mentioned. And then, yeah, basically the attention tokens are calculated within the tokens present in the window. So here it can be noted that for each window, the KV states of the old tokens are always cached, and the new KV states are also calculated and stored in this cache. So as you can see here, this is the depiction for it. And now this approach solves the main problem of, I think, execution time, where T here is basically the context length. However, there is still an issue of high perplexity due to the high attention scores, which are allotted to the initial tokens of the sequence, which we will later on explain why. And so when the window moves, these initial tokens fall outside of the window, thereby degrading the model's performance. Now, finally, the sliding window attention with recomputation is similar to the previous method. The difference is that we recompute all the KV states for each new window. So as you can see here, here we show that the new KV caches are depicted like in different colors, just for the sake of interpretability. And you can see here, this is how it's calculated. And so this method solves the issue of generating incoherent responses by having low perplexity, but it takes a lot more time as it has to recompute all the states for each token in the cache. So in the window, basically. Yeah. So therefore, the question arises, can we combine both simple time complexity and space complexity along with getting accurate responses in a single language model? Yeah.
And the answer is yes. The researchers were able to create a new LLM attention model called streaming LLM that can stream a sequence of tokens much larger than its context while maintaining prediction accuracy. So you can see an example of it here where the long sequence of inputs are fed into a baseline model on the left, and streaming LLM on the right. Performance remains stable for streaming LLM while the baseline model fails after exceeding its context length. Now, the core idea behind streaming LLM is from a key phenomenon observed in the paper that attention values are focused heavily on the initial tokens that are fed into the model. So this helps explain why model performance drops sharply when we exceed its context length, because by exceeding the context length, the softmax distribution, which predicts the next token, becomes distorted. And so to better illustrate this, let's walk through an example. So here's an intermediate matrix used for attention calculations. The keys along the top can be thought of as the embeddings of each token passed into the model. And then the queries on the left are the vectors used to extract information from those embeddings. In an LLM, each row is then softmaxed in order to perform the next token predictions. To put specific numbers to the example, we did our own experiment and took the same sentence that Niket used at the start and put it through BERT. And here you can see the first layer's KQ values for each corresponding token. The important thing to note is that even in this first layer, we can already see the attention sync behavior where the KQ values are disproportionately large compared to the rest of the tokens, along with the token that the last KQ value that the model received. So more specifically, let's take a look at this bottom row where we already have 5 KQ values calculated. If we plot that row on a graph, we can also plot the softmax on the right. And the main thing to notice is that in the softmax distribution, there's 2 main values that correspond with the 2 large values of the KQ graph. But let's say that our context window is only 5 tokens long. Then for our next prediction, we need to evict the first KQ value of the graph. And by doing this, we see that the softmax output changes from 2 large values to 1 large value with a much more uniform distribution. This is why the first token's KQ value is so important. When the model moves out of context for these tokens, the distribution of the softmax changes drastically. And because that distribution is so different, the model now has significantly fewer training examples to perform inference with. So now you're probably asking why the first token has such high KQ values. And the researchers' hypothesis is that it balances the softmax distribution. The output of the softmax has to sum to 1. So if the model gets some input tokens that aren't semantically important, it still needs some way to keep that softmax balanced. So take this example sentence where we want to predict the word blue. I love hamburgers is not related to the rest of the sentence, so the model needs a way to ignore these tokens for its next prediction. And the model therefore dumps these extra KQ values onto some tokens that it can choose to ignore in the final prediction. Specifically, the first tokens are chosen because during training, the first few tokens are always available. And so therefore, these tokens are called the attention sinks. Now, this idea becomes the core of streaming LLM to use window attention with attention sinks. This new method statically caches the first few tokens as attention sinks and then continues to use a sliding window. So for example, here we have either 1 or 2 attention sinks along with a sliding window size of 2. Now this method achieves linear memory and time complexity, and more importantly, it maintains the standard KQ softmax distribution even when exceeding context length. However, the system also raises several questions, such as how many attention sinks tokens should we cache, and whether the semantic meaning of these initial tokens even matter. So before we discuss those questions, we'll first cover the experimental setup. Specifically, the training was focused on Llama 2, MPT, Pythia, and Falcon. And training was done on 8 A6000 GPU servers with a single server used during inference. The researchers also used 2 groups of data sets. The ones on the left were mainly used to benchmark LLMs, but otherwise their experiments mainly focused on the data sets on the right. These data sets are extremely long, such that the researchers can examine LLM performance both within and out of context. And so concatenated PG19 is 100 books that are appended together. And the ARC data set has a bunch of concatenated queries that are designed to test LLM reasoning skills. Finally, Stream Eval is a custom data set that the researchers created that constantly asks for information contained 20 lines prior to that query. So in this picture, you can see that the information is highlighted in red, and 20 lines of querying later, the dataset contains a question asking for the relevant information in red. And the purpose of this dataset was to simulate real-world streaming situations where questions tend to ask about recent information. So finally, let's take a look at the experiments and their results.
So let's look at the first experiment, which determines whether the attention sinks are chosen for the semantic meaning or absolute position, or both also. So as you can see here, the window attention shows very high perplexity. But now if 4 initial tokens of the prompt are cached, the perplexity massively drops to 5.4. And but if we replace the initial 4 tokens with 4 line break characters, then the perplexity has a very little change. So this shows that the semantic meanings of the initial tokens do not matter, only their absolute positions play a major role. The second experiment explores different number of attention sinks to be cached during inference. So using different models such as Falcon, MPT, Pythia, etc., with different cache sizes, we see a decrease in perplexity when number of sync tokens are increased. So, however, going beyond 4 tokens shows very little improvement in perplexity again. So we can conclude that it is optimal to use 4 initial tokens. Now, the third experiment is where we take 160 million parameter model, which consists of 3 types of cache configurations. Vanilla sync token, where the original initial tokens are the sinks. Zero sync cache, where the zeroth token is prepended to the data. And the learnable sync, where the data is prepended with some randomized learnable token. So the key observation of this experiment is that specifically we allow the model to learn its own sync token, and it is able to achieve optimal perplexity with single attention sync token, as you can see in the graph here, right here. And while in the other configurations, it requires multiple attention syncs to show less perplexity. So in this experiment, 4 language models were tested out as mentioned here. And on the language models, basically we tested out the language modeling tasks and using different attention mechanisms and varying prompt lengths. Here you can see that when the prompt length exceeds KV cache size or even the pre-training context length, all other attention mechanisms perplexity shoots up really high, but the streaming LLMs is remaining at the baseline. So this shows that again that it can basically take in more input and give better performance. Now, finally, in this experiment, Llama models are used to compare the proposed solutions time and memory efficiency, and we can see that the cache sizes increase linearly when it comes to streaming LLMs technique. I mean, this speed increases linearly, but for the other baseline, the speed just increases quadratically. So despite its reduced latency, streaming LLM sustains a memory footprint that is consistent with the recomputation baseline. So yeah.
Cool. And so the main limitation of streaming LLM is that while it can stream a large number of tokens, it still has a very limited context window due to its window attention mechanism. So the tokens that aren't within the window have their information lost. Streaming LLM also only has a static cache configuration. So for example, as Niket just explained, the researchers determined that 4 attention sinks are optimal, but that's based on PG19. This number could be different for other data sets. And this leads into our future work. First off, to address the lost context from tokens outside of the attention window, you could add an additional sparse attention block that appends to the tokens you input into streaming LLM. This could allow the model to incorporate key tokens that it's seen before. The other idea is to create adaptive attention sinks so that the model can adapt the attention sink size and attention window size to the type of input that it receives. One other potential future work would be to incorporate streaming LLM into multimodal models. Streaming LLM could allow them to stream real-time data, for example, from sensors or videos. And a specific example could be to adapt visual QA models now into video QA models. And so the main takeaway from this paper is the discovery of attention sinks, which are hypothesized to contain excess attention values for each token's inference. By appending a few attention sync tokens into our context window, the researchers can dramatically improve LLM performance at minimal cost, enabling LLMs to stream token inputs that greatly exceed their context length. Thank you, and here are our citations.